In this section, we'll discuss the integral test. To see how the integral test works, we will we'll see an example on of the harmonic series and see how this applies and how this is related to the integral. So the harmonic series is the series that's defined as sum of 1 over n from n equal 1 to infinity. It may seem at the beginning that this series is convergent because you see that this guy goes to 0, but this doesn't mean anything, okay? Because the divergence test tells you that if this is not 0, then it's divergent. If it's 0, it's inconclusive. It could be divergent, it could be convergent. But you can see that the terms are decreasing. Fine, but this is not going to be convergent. This is a divergent series. To see it, we will try to compare it with the area under the curve of the graph of the function f of x equal 1 over x from 1 to infinity. So let's take a look at the graph here. This is the function f of x equal 1 over x when x is positive. You can see now that I'm trying to construct the area. I'm trying to estimate the area here where the when this is decreasing, when the function is decreasing and I choose my sample point over each interval to be at the left end point, then I'm gonna get an overestimate for the area. So here, for example, on the interval 1, 2, I'm choosing x1 to be the left end point. So you can see that the area of this rectangle overestimates the actual area under the curve. So this is the actual area under the curve. The rectangle overestimates it. The same thing happens here. So I'm going to choose x2 to be 2, x3 to be 3. These are the sample points that we choose in the Riemann sum, and so on. So for example, you can see the following, that 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. Do you see that sum right here? Okay, this is the sum from n equal 1 to 5 of 1 over n. Okay, and this is bigger than the integral from 1 to 6 of f of x dx, which is 1 over x dx. Because the integral from 1 to 6 of 1 over x dx is the shaded region here in blue. So the sum of the rectangles are bigger than this. And this pattern will continue. So if I have, let's say, notice that the limit here is just 1 more than 5 because I'm using the left end points for the rectangles. So if I choose, for example, to stop at k, not at 5, so this is going to be k and that's going to be k plus 1. So here's what I get in this case. So this is like the kth partial sum s sub k. That's the summation from n equal 1 to k of 1 over n. So this is 1 plus 1/2 up to 1 over k. So here it's like I have, instead of the 5, I have k here. So instead of the 6, I'm going to have k plus 1. Integral from 1 to k plus 1, 1 over x dx. Okay, now we know that we know how to evaluate this integral. So this integral is equal to ln of k plus 1. Now remember here, we are treating sk's as sequences. So this is a sequence. And actually it's a positive sequence, and that's also a positive sequence. So you have the sequence sk is bigger than the sequence ln of k plus 1. But I know that this goes to infinity when k goes to infinity. So this means by the comparison test of sequences that sk is divergent. And remember that limit of sk when k goes to infinity is the series that we want, which is the sum from n equal 1 to infinity 1 over n. So that's a divergent series. In a similar way, I would show that summation from n equal 1 to infinity of 1 over n squared is convergent. have a typo here. That's 1 over x squared. So let f of x equal 1 over x squared. We know that the area under f from x equal 1 to infinity is finite because the integral from 1 to infinity, 1 over x squared dx, converges. That's a p integral, if you remember it from the improper integrals. So we sketch a sequence of rectangles with the following areas. And here's what we are really doing here. If you just look, forget the first integral. Okay, I mean the first rectangle. What we are doing, for example, for this rectangle right here, we are taking the area and we are choosing the endpoint. Let's say this is x1 to be the right endpoint. Because this is decreasing, this is going to underestimate this area. The same thing is going to happen here. The same thing is going to happen here and here. So I'm going to have an underestimate. And the area of each one of these is 1 over 2 square, 1 over 3 square, 1 over 4 square, 1 over 5 square. So notice something, that 1 over 2 square plus 1 over 3 square plus 1 over 4 square plus 1 over 5 square. For example, this is less than the actual area. And the actual area is the integral from 1 to 5 of 1 over x squared dx. But over here, I'm missing something. I'm missing number 1 because the series I have, this is 1 plus 1 over 2 square plus 1 over 3 square and so on. So here I'm starting at 1 over 2 square. To get this one, add it to both sides. So I get 1 plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square plus 1 over 5 square. That's going to be less than 1 plus the integral from 1 to 5 of 1 over x squared dx. Now let's generalize this. Suppose that I want to generalize this last part here. Suppose that I'm not stopping at 5, I'm stopping at some number k. So what's going to happen is that I'm going to get the same formula I had. And this is... okay, sorry about this typo here, another typo. So I'm going to get this, which is 1 over 2 square, 1 over 3 square, 1 over 4 square, 1 over k square, less than 1 plus 1 plus the integral from 1 to k of 1 over x squared dx. So therefore, for each k, the kth partial sum, sk, satisfies the following inequality. Sk, which is defined by this, the kth partial sum, is less than 1 plus the integral from 1 to k of 1 over x squared dx, which can be computed here. Now we know that this is less than 2, and actually you can see now that sk is less than 2, sk is bounded, and we know that sk is increasing. The reason sk is increasing because sk plus 1 is sk plus 1 over k plus 1. So every time you are adding an additional number, like for example s1 is 1, s2 is 1 plus 1 over 2 square, s3 is 1 plus 1 over 2 square plus 1 over 3 square. So it's an increasing sequence. If you take if you consider s1, s2, s3 as a sequence, this is a positive sequence and it's also increasing. So by the monotone convergence theorem, the sequence is going to converge, which means the limit exists. So the sum from n equal 1 to infinity of 1 over n squared is convergent. It's convergent, but we cannot find its limit. I just know that it's convergent. So now we take a look at the integral test. It's very similar to the example that we just did. Notice that in the previous two examples, the functions I considered were continuous, of course, from 1 to infinity. They were positive, always above the x-axis, and both were decreasing. So you need these three conditions in order to apply this integral test. So before you apply the test, if you decide to apply it, you have to make sure that the function f is continuous, positive, and decreasing on 1 to infinity. Not necessarily 1 to infinity. Maybe the series that you want to consider doesn't start at 1, starts at 10. That's fine. From 10 to infinity in that case. But it will never be negative. I mean, the lowest value will be 1. So it says the following, that the summation, so if an equal f of n, the summation from n equal 1 to infinity of an is convergent if and only if the improper integral is convergent. So then it's going to be divergent also if and only if the improper integral is divergent. Okay. So here I'm just saying that if you start, for example, from n equal 5 to infinity, you just need to compare it with the integral from 5 to infinity. Not necessarily 1 to infinity in this case. A very important remark here also I want you to note it. That suppose that the integral, the summation from 1, actually that's also another typo. Suppose that the integral from 1 to infinity of f of x dx implies convergent of the related series. You know, in the integral, you can find the value. When it comes to the series, it only tells you whether it's convergent or divergent. And even if you can find the values, it doesn't mean that you're going to have the same values. For example, if you take a look at this problem, this is a geometric series. I know its sum, I know its convergent. This is equal to 1 over 1 minus 1 over e, which is e over e minus 1. But if you try to do the integral from 1 to infinity of 1 over e to the power x dx, okay, this is going to give you, for example, the limit when r goes to infinity, integral from 1 to r e to the power negative x dx. So this is going to be e to the negative x over negative 1. So negative e to the negative r plus 1 over e. And this goes to 1 over e as r goes to infinity. So do you see the value of the integral is 1 over e. The value of the sum is e over e minus 1. They're not the same. Okay, so if I find the value of the integral and it's convergent, it only means that the corresponding series is convergent, but its value doesn't apply for the series. For example, we're going to use the integral test here to show that the series is convergent. I think I'll just do one example, one of these two. I can do the second one. Okay. So since they want me to use the integral test, then I have to consider the function, the corresponding function. So here I have an equal 1 over radical 2n minus 1. So I consider the function f of x equal 1 over radical 2x minus 1. I have to make sure of three things first. Is f continuous from 1 to infinity? Well, here I have problem when the denominator is 0. The denominator is 0 when x equal to 1/2. This is not in my domain. So f is continuous, and always the radicand is positive when x is bigger than 1/2. So f is continuous and well defined on the interval 1 to infinity. F is positive. That's the second condition. It has to be positive, because always the radical of any positive number is going to be positive on 1 to infinity. Now, one more thing I need to verify, that f is decreasing. Sometimes it's easy to see it, sometimes it's not. Okay, to see this, one way to do it usually is just take the derivative. So f is decreasing because f prime of x is equal to, now to find f prime, I like to write f of x like this, 2x minus 1 to the power minus 1/2. So I applied chain rule, that's minus 1/2 times 2x minus 1 to the power minus 1/2 minus 1 multiplied by the derivative of the inside, which is 2. So that means f prime of x is equal to, that 2 cancel with that 2, so that's minus, and here you're going to have 2x minus 1 to the power negative 3/2. Okay, this is a positive quantity. You raise it to any power, it's going to be positive. You have this negative, so the result is less than 0. That means f is decreasing. So this means that I can apply the integral test. So what I need to do here is I need to evaluate the integral from 1 to infinity of 1 over radical 2x minus 1 dx. So this is equal to the limit when r goes to infinity, integral from 1 to r of 1 over radical 2x minus 1 dx. Here we can use a change of variable. We let u equal, actually, okay, we can do it directly, but that's fine. We can let u equal 2x minus 1, so that means du equal 2 dx. Okay, so then integral, so I'm just going to find the antiderivative here. 1 over radical 2x minus 1 dx is equal to the integral 1 over radical u multiplied, instead of dx we put du over 2. So this is 1/2 integral of u to the negative 1/2 du, which is 1/2 u to the power negative 1/2 plus 1 over negative 1/2 plus 1. So negative 1/2 plus 1 is 1/2, cancels with this, so the answer is radical u. Okay, so that means that the answer is limit when r goes to infinity, radical 2x minus 1 between 1 and r. So that's the limit when r goes to infinity, radical 2r minus 1 minus radical 2 minus 1. So this is going to go to infinity, this is 1, so the answer is infinity. So then it's divergent. The improper integral is divergent. That means that the series is divergent as well by the integral test. Okay, so it's a very good test, and it relates the series with integrals, of course under some conditions. It has to be positive, has to be continuous, and decreasing. Now we saw the harmonic series diverge, summation from n equal 1 to infinity of 1 over n squared converge. Like we had the integral of 1 over x to the power p, and we call it p integrals. So here we call these p series. So any type of series of the form this. Okay, so this is called a p series. The idea is very similar to p integrals. Okay. Theorem. The series sum from n equal 1 to infinity, 1 over n to the power p, converges if p is bigger than 1, diverges if p is less than or equal to 1. The idea is, the proof is simple because we can apply the integral test here and show that this is going to be this is applicable here. So I can use the results I had for the p integrals and apply it here directly. Okay, so if you consider the function f of x equal 1 over x to the power p. Okay, first note that f of x is continuous on 1 to infinity. Also, f of x is positive because the input x is positive. Any positive raised to any exponent is positive. Now, is it decreasing? Yes, it's decreasing because 1 over x to the power p is less than, or actually is bigger than, the next term, which is 1 over x plus 1 to the power p. And for x in 1 to infinity. Moreover, if you want, you can take the function f of x equal 1 over x to the power p, take its derivative, f prime of x, which is going to be, so this is equal x to the power minus p, so that's going to be a negative p x to the power minus p plus 1. This is a positive quantity, this is negative, so the answer is negative. Okay, so that means that we can apply the integral test. Okay, so that means the following, that from 1 to infinity 1 over xp dx, we have done this before. This converse if p is bigger than 1, diverse if p is less than or equal to 1. So then automatically this is gonna imply what we need here. The series sum from n equal 1 to infinity 1 over np converse if p is bigger than 1, diverse if p is less than or equal to 1. So this is also, as we have used the comparison test for improper integrals, we will have comparison tests now, and we will compare it mostly with something that we know. So what do we know so far? We know the p series, we know when they converge, when they diverge. We know also the geometric series, and we know like some special ones like the telescoping series.